Okay, so in this video we're gonna cover following topic, which is structural design in VHDL. And I think the most important command is the format directive. Okay, so let me just briefly explain to you why this is useful or important. So usually, so far, you have been designing some simple code. Right, just a few logic gates, right? And the whole design fits in one single VHDL file. Okay. However, what happens when the design increases in complexity? For example, I have here one. What if you have, let's say, a bunch of different blocks? Let's call this, I don't know. You design your circuit A.VHD, another circuit, let's call it B.VHD, and another circuit, let's call it C.VHD. And the top file, I guess for lack of a better name, let's call it top VHD. And well, inside the circuits, they interconnect with each other, right? Maybe the outputs of these blocks, or this block right here connects to the input of the next, maybe, or maybe here connects right here. This one, the output here, might connect to the output of the entire circuit. The output here might also connect to the output of the entire circuit, and the input here go right here, and this input right here. It doesn't have to be that way, by the way. There are many ways for this to happen, right? It could be, say, that this output, right here, also somehow, for some weird reason, goes also onto the input of this circuit. Okay. So in order to do all of that, we need to use what we call the format directive, okay, to interconnect the individual circuits among each other. One example, even though this is kind of silly, is to create a different file, let's say for each, in this case, logic gate, right? Like this AND gate, NOT, and OR gate, and then interconnect them all. I think it's kind of not a good idea, because you know that we can just use one file to interconnect them all together, right? We don't need to do any formatting here. However, think about this example. This is called a 4-to-16 decoder based on a 2-to-4 decoder of several of them, right? 1, 2, 3, 4, 5. So if you were to connect these circuits right here this way, you would implement a 4-to-16 decoder, okay? But in order to do all of these connections, you need to now use again the format directive, which, by the way, you are sort of familiar with it, because we also use it for test benches, right? As you know from your previous labs. Okay, so this is one example. There are far more complex examples. For example, this is a specific microprocessor, right? And every block right here, right, can be huge, right? And interconnects to other blocks right here, like this controller interconnects to these registers, then these registers interconnect to the ALU, or a set of registers in the CPU, right, and so on. And each one of them, by the way, can be inside, different blocks. Let me do this. It could be that each one of these blocks, right, it could be that each one of these blocks is itself, right, made out of smaller blocks. Like here. Let's just do 2, so it doesn't get so confusing. Okay, and you can call each block, I don't know, p.phd, for example. That could be that. Maybe the font is too large there. Let me see. It's better, I think. Right. Oops. Give me a moment here. I will fix this right now. Okay. Okay. So that could be p.phd, and this could be, say, q.phd, right? And inside, of course, they also interconnect, right? Like the output of this block might be the input of the next one, right? And this output right here might be connected to here, this one here, for example, and this one here. Okay, so this kind of design, where you have a bunch of blocks, right? It's called a hierarchical design. Right? This is all that we're going to be learning today, using the format directly. And again, you will use that until the end of the semester and beyond, right? If you take the next class, the EC 4710. Okay, so how do we do it, right? What's the procedure? Well, in these slides, there's an example, right? And I think I'm going to use first a different example, a slightly simpler one. Okay, some of you, or many of you, might have already seen this example. Let's see if I can hide it, if I can find it somewhere. Yes, this one here. Okay, so we are going to do the following. Just in a moment here. Okay. So I assume that most of you have heard of the famous, adder, right? The adder circuit, which is made out of smaller blocks, which are called full adders. Don't worry about the mechanics of this, because we're going to learn that later. But the important part here is that these full adders are these tiny blocks here. In fact, I think the file name, I think it's fulladd.vhd. And we use not just one of them, but we use 4 of them to create a 4-bit adder. And based on that, we create a larger block, right? Which is the 4-bit adder, for example. So, what's the procedure, right? To create this. To do it using what we call the structural description in VHDL. We're gonna have essentially 2 files, right? The fulladd.vhd, which is the description of a 1-bit adder, right? And the top file, right? Which I'm gonna call it my add.vhd. That's the top file for in this case, 4-bit adder. And I assume you have heard how this circuit is built. I have it here in the slides, by the way. Let me see if I can find it. Maybe not, but I think it's in your lab number 2, I think. Let me try to find it. For example, here, right, this is the full adder circuit, right? You have to do, by the way, something very similar in your lab number 2. It is just that the circuit is larger. But look at the full adder. It is just a bunch of logic gates, right? Essentially 3 AND gates, 2 XOR gates, and 1 OR gate, okay? So how do we describe this circuit? Well, it's easy to do it, right? So far with what we know. We just use this VHDL code here, right? This code will implement this circuit, right? With 1, 2, 3 inputs and 2 outputs. So this is a simple circuit built out of logic expressions. So I don't think this is going to pose any problem. The problem is the next part, right? And my add.vhd, right? Because that's the one that it will interconnect, you know, the individual 1-bit adders. So let's do that, okay? Using you know, Vivado. So for this experiment, what I have done, essentially create a new folder. Right? I already copied and pasted this file because it's already, you can download it, by the way. I created a top file, right, that I'm gonna have to edit, right? And then I also, you know, use a test bench. And the XDC file, just in case you need it, in case you wanna actually test it on the board. So remember what I said last time, right? This is the way you should proceed. Always first create the folder with your files, even though they might not be completed, but at least create, you know, the template. Right, and now you open Vivado and create a new project. And here, the project is called my_add, my_add. There you go. You know, don't change anything here. Make sure that, of course, the language here is VHDL and not Verilog. Don't add anything. And here, well, just go for the chip, right? I think, again, if I am not mistaken, that should be just in a moment here, because it's different every time. I just want to make sure that I have the right one here. This one should tell you the exact component. Let's try to find it. I think we already did this, by the way, but right here, the A750T. Right, CSG324, that's the package, right? Okay, and then -1, and then 50. Okay, so now we're ready. Let it, you know, do its thing, and now we're gonna add these files, right? All of this into the folder. Let me delete this one because this file belongs to a different board, and X is for DDR. Let's just use the master file of the A7 board, right? Okay, so once you are in Vivado, what do? You just add the sources, right? This is pretty simple. Let's go to the folder, right? And first add the design sources, which are, of course, just the circuit itself, right? Finish. And then you can add, if you want, the simulation sources. And of course, you go for the test bench. And then you can add the constraints, which is the XDC file. There you go. So now I am ready to edit, right? Okay. I mean, depending on how you actually, you know, do this, might get weird names. But here, for example, I have the full adder already written for me. I don't have to do anything. But now the top file, which is supposed to call my add.vhd, has a different name. Well, and the reason is that, of course, you know, I am not going to start from scratch. and you shouldn't either, I use this example here, which is slightly different, slightly more complex to be fair. So I just use this code here, right? So, but for my new, example, I am gonna edit the code, and it's better, I think, to start over. Let me see. Yes. So here, I'm gonna forget about all of this, delete that, and I have to change the entity, right? This one has to be my underscore ADD, and the output for the same. Okay. Please, like I said in the last video, do not pay attention right now at this online error thing. Okay, it will get you confused. First finish what you have to finish, and then you might pay attention to it. You might. Even at that point, it might not be a good idea anyway. So, the circuit. As you can see, the circuit, we first have to define the entity, right, of my add.vhd. We have to define the inputs and outputs, right? And we have, actually, I would say only two inputs, right? X and Y in this circuit, remember? Because this is the full adder, the 4-bit adder circuit. So we have X and Y, we don't have this input. And that is a vector, right, of 4 bits, each one of them. We also have an output S, right, also of 4 bits as a vector. Then there is an overflow. Let me see. If I remember correctly, when you add two numbers, I think, let's do that. If you want to, just to give it more, I guess, flexibility to what you're doing, let's include an extra input in my circuit. And let me call that carrying, right? That's my adder, right? My 4-bit simple adder, unsigned, right, by the way. I will cover this another time. So we have the carrying, which is just a simple bit, right? And then we have, of course, the overflow output and the carry out output, which, by the way, they happen to be the same bit, by the way, okay? So, and then in the structure, which is the actual, architectural description, remember, what you do? I'm gonna delete all of this, by the way, so it's not, we can start over. Yeah, let's delete all of this too. What do? We have to use this entity, full adder. So I'm going to copy and then paste the entity right here on the architecture. Right. And remember, what's the trick here? You rename these two components. I think you get rid of the IS, and then at the end, you do component. If you do that, you can actually use this component in this top file. Okay? And now we're going to start actually building our circuit. Okay, so the key here, and there are many ways to do it, but the key here is to realize that you might need some internal signals. Like, think about these individual carriers, because to connect the output of this full adder to the output of this another full adder, you need an intermediate signal. Okay, so let's do that, right? So that will be here, just a signal. And then let's call it C. That's type standard logic vector. How many bits? 1, 2, 3, 4, 5, right? It's always one more than the other, than the size of the full of the other. Okay, 4 down to 0. What else do we need to do? Well, Now, let's do the simple things. For example, we say that C0, this bit is the same as carry in, right? Oh, that's pretty easy, right? All I have to say is that C, remember when we did how to address individual bits in a vector, C parenthesis 0, and then that's carry in. The same for the output, by the way. Overflow, which is the same as carry out, is actually C4. So let's say C out is C4. And the overflow, well, you might want to do this, right? It makes sense, but remember, it doesn't work, right? It's because both of them are outputs. Just use the same bit, carry out. Okay. C4, sorry. So having said that, that's, I think, most of what we need to do, as we said at the beginning. And now we have to use the port map directives. So if you go here to the slides, let me see. This is how it's going to work. You see, port map. You have a bunch of signals in the port map, a bunch of signal declarations, and each of them on the left, right, is the signal name in this particular example in the full adder circuit. And you want to do the following. You want to connect that particular signal to a signal in the top 5. Okay, that's just one signal, by the way. Of course, you know, a circuit has a lot of signals, right? So you will have a lot of different connections as well. Okay, so that's more or less how this works. And well, let me try to do it for this example. Let's see. If I want to use, for example, let's now use this as F0, F1, F2, F3, because that's, I'm going to use this as my labels. Okay. So F0, remember, is just a label, by the way, that this requires, unfortunately. And then you use the name of the circuit. In this case, is that. And now you say port map. I am going to connect. Okay. The idea is usually to follow, you know, this, right? So we say, well, carry in is going to be connected to something. X the same, Y the same, will be connected to something, right? S the same, and there is a carry out the same. And that's all. That's how you connect the first one. But of course, we need to now indicate what is going to be connected, right? Right here. That's those are the signals in the top 5, right? Now, we'll have to look at your circuit diagram. So this carry in right here, right? That belongs to the full adder circuit, right? Remember, because all of them are the full adder circuit. It's just that we are using several instances of it. That signal is carrying, and it's already right here. This carrying. See, it has to be connected to the C0. This is the signal in the top 5. Oh, well, that's what we do. C0. There you go. Right? What about X? Well, the X input right here has to be connected to the signal X0. Right? There you go. What about Y? The signal Y has to be connected to the signal Y0. And you can see where this is going. This is pretty simple right now. It's the output S must be connected to the signal S0 on the top 5. What about carry out of this individual full adder? Well, has to be connected to C1 because we can't actually connect this carry out to this carry in directly because we can only connect the signal in my block, in the tiny block, to the signal in the top block. Okay? So we need an intermediate signal, right? That's why we have C1 there. And there you go. That's what you do. Okay? That's the first. That's how you connected the first, circuit. If I want to show you, I think a better way to show it is this. Look at this. Essentially, this directive, all that it is doing is interconnecting, each one of these, wires, right? Like C1, carrying is interconnected to carry 0, right? There you go. This connection is made at that point. The same for X2 with X0, Y with Y0, S with S0, and carry out with carry 1. Okay? Well, now we can do the rest, right? I think it's pretty easy now, because now we're going to focus on the second one. Okay? Let's see. Now we're going to focus on this one here, right? So, let's see. Yeah, let's focus on this one, okay? So now for the second one, well, it seems to me that it is going to look pretty similar. I have to use a different label, of course. But now carrying is now connected to C1, right? And that's how you, in the end, are interconnecting this carrying right here to this carry out, right? That's how you complete that connection, by doing carrying with C1. Okay. What about X? Well, X belongs now to X1, right? On the top file. Y, Y1, S1, and then carry out now will be C2, right? And as you can see, this thing is going to repeat over and over. It is actually very repetitive. So this X2 to the same, right? We just need to change now here to and the carry out now is carry 3. And the final one, which is F3. 3, 3, 3, 3, and this is now 4, right? Yeah. And I think now you are, done. Okay? That's how you connect all of them together. But yep, I think this is it. So now, the next step, of course, I'm pretty sure this is going to work, but just to make sure, I am going to actually use this circuit into the test bench, right? And the test bench, remember, is kind of the same idea, right? It is just that it is not a circuit, right? But still, we are treating them as a component inside the test bench, right? So we will treat our main circuit, which is called the unit under test, by the way, as a component, right? And remember, always use the same names. I prefer to use the same names for the inputs X and Y. Let's do 3. For the outputs S32. And now we do the port mapping. Remember, now you see why this was used before, right? Because we were doing the same thing. It is just that we were not interconnecting circuits, but we were interconnecting our main circuit to the test bench, okay? Oops. Well, it requires you, remember, don't forget of any signal. This is carrying, it's going to be connected to carrying. But of course, I have to also create carrying, right? In a test bench, by the way, you can do this because everything is temporal, right? This is we initialize here it makes sense here carrying with 0 in the test bench, by the way. Only in the test bench. You can only initialize in the test bench. You cannot initialize the architecture at all. Okay, so now we're good here, right? You can see, I hope now this part is clear as to why we use this port map in the test bench, okay? Essentially, the test bench is just what you think about. You can think about the test bench as another block, a huge block, right? With no outputs and inputs, only internal signals, by the way. And this will be the test bench, okay? So that is the test bench, okay? Let's use a different color here. Okay. So, but the difference is that the test bench, it is not a circuit, right? It is just a file that allows you to fit stimuli onto your circuit. Remember, this test bench has no inputs and outputs. Okay. So now of course, we do what we call the stimulus process, and forget about that for now. I'm gonna delete this because I grab this from a different file, and I can do the following. Oh, no, that didn't work very well. Keep missing the right command. Yeah, there. So we're gonna use just carrying first equal to 0. Forget about this, because this belongs to a different file. And here carrying equal to 1. And we provide, of course, you see, at every time different inputs, right? In the hope that we can get different outputs. And I think that should do it. So now what is the next step? Well, if you want to test this in the board, right, you need to use what? 8 switches as the input, right? 4 LEDs as the output, 1 switches as the input, and 2 more LEDs. So essentially we need 9 switches as the input. So we're going to just use the first 9. So let's say, we're going to say here y 0. Remember, in the XZ file, you have to use, instead of a parenthesis, you use a bracket. Okay, that's the only difference. X is here. And that would be x0, x1, x2, x3. And here, of course, this is the carry. On the LED side, we have 6 outputs, right? Let me double check. Yeah, we have 6 outputs. So that would be S0, S1, S2, S3, and then carry out and the overflow. And I think that should do it. Okay. So now it's time to, first of all, remember to synthesize to make sure there are no syntax errors or warnings for that matter. So in this, by the way, in the slides, what you have is a slightly different example, a more complicated one. This is called a 4-bit adder subtractor in 2's complement representation. The only difference is that we have to add some XORs here. It's a slightly more complex circuit, but it is actually the same idea, right? You have the full adder here, and then the other 4-bit 2's complement adder, right? Which requires you now to what? We need to, for example, here, we need to define this signal here. Let's call it YT for lack of a better name, right? And the carry out and the overflow is actually the XOR of the 2 previous carry outs. Okay, and there's another signal called add sub, right, which is the input to the XOR gates and also the input of the carry C. So you have to do all of that, okay? But it's the same idea. Okay, so this thing run. Remember, always look into the project summary to see if there are warnings. This warning, you don't worry about it. And now the next step is to do simulation, right? Hopefully, if we did everything right, we shouldn't get any issues. Let's simulate that circuit. Okay, as I was explaining before, this circuit here is slightly more complex, only because we have these XOR gates. Okay, but I'm sure you can figure it out very quickly, right? This carry out is just the same as add sub, as you can see here. Oops. Yep, C0 is the same as add sub, for example. Then what else? Overflow is just the XOR of the two previous carries. YT, each individual YT bit is just the Y bit XOR the signal add sub. But then everything else, remember, in the port maps is the same, right? Except that we use YT instead of Y. Okay. You can download this. By the way, this example too. By the way, I prefer to use this simpler example in this video. I believe it is simpler. Okay. Well, this thing seems to work, or at least looks like it. For the most part, like I mentioned, you will spend a lot of time here in the simulation waveform. Let's see. Okay. So we can double check, for example, if you do f plus f, which is 111 plus 1111, you will get something like a 11110, something like that, I think. Okay, I think it's better if you look it into in terms of. No, it's not gonna work. Let me see. Okay. And you can change the radix. I'm gonna show it as binary, or if you like an unsigned decimal. There you go. You see this 1111 plus 1111. If you remember from your previous class, right? It's actually if you add simple unsigned numbers like this, what do you get? You're gonna get the following, right? So you have, but we only have 4 bits for the other, so we need to use the extra bit that will be our carry out or our overflow. This is why here you have a 1, right? And you can check, by the way, each case, and all of this happen with carrying equal to 0. Okay. Note that it might help in the end to also, I guess, change the color of the signal if you want to. Okay. And this is with carry in equal to 1, which is a little bit different, right? Okay. And I think this works. This works fine. If you want to keep these settings again, you need to save this configuration waveform. Okay. Not only that, you need to add it to the project right here. So next time you simulate, it will save these settings. Okay. Or something else that before I forget, because every time we forget to mention. In many cases, even though this example is pretty simple, but in many cases it might be very useful to look at the internal signals. In this case, we only have C. It's internal. And by default, C, as you can see here, is not shown in the waveform, right? So what do? You have to go to scope, right? Test bench, UUT, that's your circuit, right? It will show you all the signals, inputs, outputs, and internal signals. And you can see here the C. So all you do is right click and you add to the wave window. And it will be added. And of course, you need now to restart. I think we did this last time. You use restart. And you can run it for, say, let's do it for less than that. 800 nanoseconds, for example. And there you go. But you see, you can see the bits. By default, It's not going to show in binary, so you have to change. Okay. So when you are dealing with a large circuit, this looking at the internal signals, right, might be very helpful to you. Okay, especially say in lab number 2, for example, your job is to build this circuit, but it might be that on the first time it's not going to work. That's actually more the most likely outcome. So, for example, you can look at C0 and C, right, to see if they're okay, to determine whether this, where the mistake is at. And I think, in fact, this is what I'm asking you to do in the lab sheet, by the way. Okay? So, so now we're going to save this, right? And then we close the simulation window. Okay. And now, as a bonus, before we go, one important thing is the following. And so far, what we have shown, right? If you can see, this is a 4-bit adder, right? And you can say, well, what if I want a 5-bit? Well, I would think it's very similar, right? I just need to copy an extra line, right? If I wanted a 5-bit. Just a moment. Here. If I want 5 bits, I need to, I guess, make this C5, change here the number here, change the number of bits here, and then add another line here, right? That would be simple. What if I want 6? Same thing. What if I want, as is common, right? Let me see. Turning it into a 5-bit adder is simple enough, right? But what if I want, for example, like it's common nowadays, a 32-bit adder? I guess it is possible, right, to copy, and have 32 lines of code. But as you can see, this thing starts getting very repetitive. So there is some approach that you can use to simplify this. I call this something like a small introduction to, a generic programming. So I'm going to use what we call a for generate statement, okay? Because this is very repetitive, right? So one, I guess, mistake that is commonly made, that this is not a loop, right? A loop in software consists of several loops where each one depends on the previous one, usually. Here, this is actually a repetition of a statement. And each, index, right, or each, let's call it in a way, iteration index, for lack of a better name, generates, in this case, a full adder circuit. Okay? It is not a loop, by the way. We call it for generate. We're just repeating this 4 times. Why is it not a loop? Because remember, the order in this case doesn't matter, right? If you remember, I can always do this, right? And it would work the same way, right? Because we are using concurrent programming, right, in VHDL. So let's do it. So how do we do this in a generic way? Say, well, carrying. Well, it seems to be that this, instead of 1, I use I, right? Because for the first one, and then send I here, I, and I here. And here I use I plus 1, right? Because that's what I have noticed by looking at this pattern, right? It is relatively easy to note that, this is carrying Ci, and this is Ci plus 1, right? Well, I guess, sorry. To avoid confusion, I'm going to go back to where it was before. So that's much better. So there you go. Carry 0 and carry 1. And then here carry 1 and carry 2. So you can see, to complete this for generate, you need to find the repetitive pattern. In the case of full adder, of this 4-bit adder, it is actually very easy to find, right? It's just CI plus 1. But there are other cases in which this is actually very, very hard. Okay, so it works in some cases, in other cases it might not work as you expect. Okay, but it is nonetheless very useful. Okay, for you to do all of that. Okay, so what else should I mention before we go? Well, another thing you can do is to actually do the following. Let me just quickly do it here, because you might find also this very useful in the test bench. Usually it would be nice. How do we test a circuit usually? Well, we try out with some variables, right? We try out some cases, and based on that we the idea is usually the best way to test a circuit is to try out every single possibility. Know that here, by doing this, we didn't actually try every single possibility, because there are too many, right? Because we have 9 bits, so that would be 512 different possibilities. So instead, this is what we plan to do. We can use, and this is actually a for loop, because we're in the test bench, right? And everything is temporal. So now we can actually use what we call a loop in the test bench. Okay. So we're gonna do for I in 0 to 15, right? And for j in 0 to 15, we're gonna do the following, right? Ideally, we would like to do this. We wanna have, for example, the signal y. I want that to be equal to I, right? And then the signal x, I want that to be equal to j. And that's how we cover all of them. But of course, never works as easy as that, because the problem is that I is an integer, right? And y is actually a vector of bits. So we need to use this conversion signal, which converts the signal I, which is an integer, using 4 bits. There you go. And the same here for the j signal. Okay. How do we use this statement here, the conversion statement? Well, you have to use this library, right? This is for count, still logic vector. Okay. And of course, you have to try this. Don't forget about the carrying. You first try with carrying equal to 0. And now you're going to repeat the same thing. Oops. Yeah. Again, you repeat it. But now you repeat it with carrying equal to 1. Okay. I think, let me see if I have it right. Yeah. Well, if this is GI, I mean, you shouldn't have a different GI. This is just, it doesn't like you to have that. BI, for example. Or TI, for example. This one actually doesn't matter because it's inside the TI. But if you want to make sure, let's call it TJ. Okay. So now, I think, this will test out, every single possibility. Right? Remember, it will look like this. It will try out 0, 0, 0, 0, 0, 0, 1, all the way to 0, 0, 0 to 15, right? And then it will start over. 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, all the way into 15. Okay, that's what this loop it's doing. Okay? If you want to double check, well, let's see. Hopefully I didn't make a mistake, so let's try to simulate, right? Maybe. Because it is possible that you make a mistake too there. Just give it a little bit of time until it finishes, okay? Okay, so now it actually worked. And as you remember, like I said last time, right, the settings, right, were kept, right? So and we have here all the possible cases, right? You just look carefully inside. Oops, let me see if maybe I got something wrong here. Uh, 001. Okay, so there was a small mistake actually. It's a tiny one in my test bench. For some reason, let me see. I included here another weight when I didn't need to. Okay, even though even though the slide says so, right? I think, by the way, this is a mistake. To be fair, I just checked, and actually, if you download this file, this statement does not exist anymore. Okay, but this thing cost. I mean, just the that thing cost. There's a slight mistake, actually very hard to detect in the test. I mean, I wouldn't call it a mistake per se, but something that we didn't want to. It cost, let's say, 001 to have 1111 for an extra 10 nanoseconds, for example. Okay, and we want to start over, right? 000, then we go 0001, and then we 000. If we want that, of course, we need just this. Okay. Again, I'm gonna fix this, but this line. But by the way, in the code that you can download, right? You can actually, you won't find this line. Okay. And I think, to be fair, that's most of what I wanted to show you. If you're curious, you can, read into what is called parametric coding. Like if you want to generate a, an adder of any number of bits, and all you need to do is to modify, this parameter. You use something called generic, and then everything depends on n. Right? Look at that. Okay. Even the test bench, you need to also include the generic, right? And everything depends on n. Instead of 15, we use 2 to the n minus 1, for example. Okay, but by the way, we are not doing parametric in this class at all, by the way, so don't even worry about that. But if you're curious, of course, feel free to do that. There are more, by the way, more examples, like the array multiplier, okay, or the ALU, right, and the 626 LUT. But I think the most important one is this, okay, the 4-bit, like in our case, the 4-bit adder. And again, please, if you understand this, I think you are in a good track, to complete the labs in this class, because everything depends on that, on port maps. You will see that until the end of the semester. All right? Thank you so much.